Welcome everybody back to our course on memory device technology for AI/ML computing. I'm your instructor Shubhadeep from IIT Hyderabad. So last time we began our study of magnetic RAMs or MRAMs. So let us do a brief recap of what we studied the last time around. First, we introduced the spin degree of freedom, and we saw how spin can be used to store and manipulate information, and that is done by breaking the so-called spin degeneracy through the application of magnetic fields. The key advantage of using spintronic devices was the promise of having low power operation. This is because spin currents are inherently dissipationless. Next, we also looked at the phenomena of GMR or giant magnetoresistance. In GMR, we had a device stack of a non-magnetic metal sandwiched between two ferromagnetic layers. And we saw that the GMR effect is this particular device has high resistance at zero magnetic field, and it goes to low resistance when you start applying a finite magnetic field. We also saw this is due to the fact of spin dependent scattering, where if the magnetization of the two ferromagnetic layers are in anti-parallel configuration, they experience large scattering from both upspin electrons and downspin electrons, which are part of your charge current. However, if they are in parallel state, they experience low scattering from one of the spin configurations. Therefore, the anti-parallel state we saw was in high resistance state, and the parallel state was in low resistance state. So furthermore, we also saw there was a need to move from GMR based devices to magnetic tunnel junctions, MTJs, and this was because the magnetoresistance percentage sensitivity in the case of TMR devices was much lower compared to GMR devices. Okay, and these magnetic tunnel junctions are at the heart of all magnetic storage technology and also MRAMs. So it is very important to understand these MTJ devices. So let us begin our class with the most successful commercialization success story of magnetic tunnel junctions, which we all have used in our HDDs or hard disk drives. This is a widespread technology. So magnetic tunnel junctions are widely used as sensors in the read head of modern day hard disk drives. So this is the read sensor which goes inside the read head. So as we saw in our previous class, MTJs consist of two ferromagnetic layers which are separated by a thin insulating tunneling oxide. The pinned or the reference layer has a fixed magnetic orientation, whereas the free layer is free to align itself to stray magnetic fields. Where are these stray magnetic fields coming from? They are coming from the bits that are stored on this rotatable disk. So as the read head passes over the disk surface, this stray magnetic fields from each of these bits changes the orientation of the free layer. Okay, and as the free layer orientation changes, the resistance of the MTJ transitions from high resistance state to low resistance state, depending on whether it is in anti-parallel configuration or parallel configuration with reference to the fixed layer or the reference layer. Okay, so by measuring these resistance changes through the external peripheral circuitry, we can determine whether the bit is corresponding to 0 or it is corresponding to 1. Now these MTJs are very, very compact, very sensitive and scalable, and this has enabled today's high density magnetic storage. However, it is very important to note right at the beginning that unlike what we had conceptually seen, that MTJ consists of three functional layers: the fixed layer, the tunneling oxide, and the free layer. Actual MTJs are much more complex. The number of physical layers in an MTJ is sometimes even greater than 40. Okay, so you see here one of these diagrams of a magnetic tunnel junction. So actual MTJs consist of many more layers, but they can be subdivided into 4 main categories depending on how they help the MTJ give very large TMR percentages. So optimized MTJs nowadays can give TMR percentage of 400 to 500% also. The first layer is combination of the seed layer, the synthetic anti-ferromagnetic layer, and the pin layer. And the job of all these three combined is to stabilize the magnetization of the reference layer. The second thing we are very familiar with is your tunnel barrier, which enables your spin dependent tunneling. So as we had seen last time also, the optimized material nowadays used is magnesium oxide, and that has a particularly favorable crystalline structure or rock salt structure which promotes spin polarized tunneling. This means that the electrons spin interact with the magnetic states of ferromagnetic layers much more efficiently and is responsible for very large TMR effect. We also saw the free layer, which is more like a soft magnet. This soft magnet is made up of a compound consisting of 3 elements: cobalt, iron, and boron. Finally, we also have something called the capping layer. The job of capping layer is to protect the crystallization of this entire stack. Crystallinity is very important for good magnetization properties. As you can also see through some of the numbers, to get very good MTJs, you need to deposit these several materials with atomic precision. So this deposition of 0.5 nanometers, 1.5 nanometers is a real feat in materials engineering, where you are depositing few atoms thick functional layers uniformly throughout large wafer scale devices. And this is why I say that the development of MTJs was a true testament to scientific and engineering feat. So successful commercialization, the scalability, very good bit density, and very low cost per bit is ultimately what helped penetrate HDDs to each and every computing device, and that is why the GMR effect won the Nobel Prize. We had discussed it last time. However, in the context of ENVM space or storage class memories, these HDDs or this technology is not good enough because the speed is very, very poor. It is 100 milliseconds. And also the endurance is only 10 to the power of 3 or 10 to the power of 4 read and write cycles. All of this is because you have mechanical moving parts, a rotating disk. And this is neither good for speed because it gives you sequential access, nor is it good for endurance. So the idea is, can we have magnetic random access memories for electronic non-volatile memory applications or storage class memory? For this, you need very fast memory and very dense storage. In order to achieve this, two things have to be improved over the HDD paradigm. The first is that you need to have random access. In order to have random access instead of sequential access, you need to integrate these devices on a cross-bar array with word lines and bit lines. The other important aspect that we need to look at, that the control of magnetization has to be completely solid state. It cannot consist of mechanical moving parts. You would want the control of magnetization only from electric fields. So the first generation of these MRAMs, which were also called field MRAMs or toggle MRAMs, were developed in early 2000s by several companies such as IBM, Freescale, and Everspin. So let's look at the device level implementation of a field or a toggle MRAM. At the heart of a field or toggle MRAM is again your magnetic tunnel junction. So a magnetic tunnel junction, as you can see, is your main storage element, where you have the pinned layer where the magnetization is fixed, and you have your free layer where the magnetization can change direction and come to either the anti-parallel state or the parallel state. We have seen several times that the anti-parallel state is high resistance, whereas the parallel state is in low resistance. So for this kind of a storage element, the read path is same as what we have been seeing for any 1T 1R configuration. You have your word line. When you enable your word line and you apply an appropriate voltage on the bit line, depending on whether this device is in high or low resistance state, the read current is reflected, which is compared with the reference value. And if the read current is above the reference value, of course it is in LRS, otherwise it is in HRS. So the read configuration is very simple to understand. What about write? In write, as we understand, you have to flip repeatably the magnetization of the free layer. How do you facilitate the flipping of the magnetization or majority spin direction in the free layer? This is done by a principle which all of us have studied in our high school physics. It is done by using something called Oersted fields. Remember, whenever there is a current carrying conductor, it emanates out magnetic fields. These are called Oersted fields. So this is what is the principle of doing write operation in field or toggle MRAMs. As you can see from the schematic, this write word line is built such that it is going inside the plane of the paper or inside the plane of the slide. This is what this kind of schematic means. So how do you change the magnetization? Essentially, you play with the direction of current that is flowing through this write word line wire. As you can see from the right hand thumb rule, if the direction of the current is inside the plane or inside the slide going from me to you, then through right hand thumb rule, please look at the camera, the magnetic field which will be generated is in clockwise direction, as you see over here. If the direction of the current is reversed, it is coming from you to me or away from the plane of the paper, then the direction of the magnetic field is in the anti-clockwise direction. Therefore, by toggling the direction of the current, you can change the orientation of the magnetic field, and therefore you can flip the reference layer's magnetization from left to right or right to left. But important to recognize here is that because of this nature of device implementation, the read word line and the write word line are separate, as you can see, and also the paths for read and write are entirely separate. Okay. Another thing to recognize is that the write currents which you have to apply on the write word lines are generally large. They are in the orders of hundreds of microamperes. This is because the Oersted fields that are generated, B is equal to mu naught I by 2 pi r, this constant of proportionality, which is also called the magnetization permeability, mu 0, is a rather tiny number. So to get reasonable magnetic fields, you have to apply a large enough current. Okay, so with this, let's look at the array level implementation of these devices. So here is the schematic of the array level implementation, and here is a cross-sectional SEM image which is done at the 180 nanometer CMOS node. It is very revealing to show that this is the tiny MTJ. The MTJ area is actually very small. Rest of the area is occupied by your access transistor. There is also a separate word line for write. This is the write word line. And the right word line, because it causes the magnetic field, is situated very close to the MTJ, whereas the read word line is connected to the gate of the access transistor. So this kind of array level implementation was demonstrated by several companies like IBM, Freescale, Everspin, and there are several chips that came out, but they were primarily for niche embedded applications. The capacity that these chips could have was rather small. It was 8 to 32 MB to qualify for mass storage, and therefore they were used primarily for embedded applications for niche areas such as aerospace, automotive, and also military systems. This is because spin based storage and logic is generally immune to radiation effects, and that is why military and aerospace systems which are exposed to outer surfaces of space generally prefer spin based devices for better reliability as compared to charge based devices. However, the scaling of these toggle or field MRAMs was rather challenging. You could only go to 50 to 100 F squared. Not only that, the smallest feature size or the smallest logic node beyond which it became very tough to scale these MRAMs was the 90 nanometer node. Why was this the case? The primary reason was that the write currents that were being applied were so large that they were causing a lot of power consumption. Not only that, from our understanding of previous ENVM devices or non-volatile memory devices, you can understand that field or toggle MRAMs will have a huge extent of write disturb. This is because suppose this particular selected cell, you need to change the magnetization, and that is how you will do through the write word line. The magnetic fields which are generated by the write word line will cause some disturbance in the magnetization of the free layer of neighboring cells also. So this write disturb and large write current prevented the proper scaling or good scaling of these field MRAMs. These field MRAMs showed indeed that creating MRAMs or creating magnetic based random access memory is possible, but there was a big question mark on whether this technology can be scalable. Everything changed. A new hope came about when there was the discovery of a game changing technology or concept called the spin transfer torque. And the promise of spin transfer torque, as we will see soon, is the complete and direct electrical control of magnetization or spin direction, majority spin direction in the free layer. One of the interesting things about STT is that first it was predicted in theory. The exact theory was developed in 1996 by researchers at IBM and at Carnegie Mellon, and the experimental demonstration actually came few years later. So what is spin transfer torque effect? So spin transfer torque is a phenomena where a spin polarized current. What is spin polarized current? Spin polarized current is that where majority of electrons have a preferential spin in one particular direction, either up or down. This is unlike charge current. Why is it unlike charge current? In charge currents, there is no preferential spin direction. 50% are in upspin and 50% are in downspin. So what does this spin polarized current which have spin which is oriented in one direction do? What it does is, upon entering a magnetic material, it can alter the magnetization of the magnetic material. Suppose the magnetic material has a polarization in the up direction. Imagine lot of spin polarized current which is in down direction enters this magnetic material. What can happen is, because there is a spin angular momentum transfer from the electrons of the current, this can flip the magnetic moment of the material, causing it to change. Okay, so Main question, however, is how do you generate these spin polarized current? This kind of spin filtering for our purpose happens at the edge of a normal metal and a ferromagnet. So the actual phenomena with its quantum mechanical details is a bit more complicated, but for our course it is enough to understand that if a charge current, look, this is a charge current, half of the electrons are in upspin, half of the electrons are in downspin. So a charge current is trying to enter from a normal metal to a ferromagnetic metal. What happens is that the majority spins are preferentially transmitted. What is majority spin? The spin which has the same alignment as that of the magnetization of your ferromagnetic layer. So ferromagnetic layer here has spin in the upward direction. The spins which have up direction are getting transmitted. See, all the up spins have got transmitted, whereas the minority spins are preferentially reflected. And this is the principle of generating spin polarized current, or also called spin filtering. Okay, so how does it help in our magnetic tunnel junctions? So in our magnetic tunnel junctions, the spin filtering happens at the interface of your hard ferromagnet or pinned ferromagnet and a normal metal, or the interface of MgO. So let us understand this with the actual set and reset cycles. First, let's consider that the magnetization in the soft ferromagnetic layer or the free layer and the pinned layer is in the same direction. Since this is in parallel direction, this device is in the low resistance state. To a device in the low resistance state, we apply a current which is in the negative x direction, as you can see over here. So the current is flowing from the hard ferromagnetic layer to the soft ferromagnetic layer, or the pinned layer to the free layer. As you know, electron conduction is in the opposite direction to your conventional current. Therefore, we will see through this animation what happens when a charge current, see, this is a normal charge current going from right to left, and these are electrons which don't have any preferential spin direction. 50% of them are in upspin, 50% are in downspin. What happens when you flow a current through this particular magnetic tunnel junction? What happens is, as you can see from the first part of the animation, the spins which have the same direction or majority spin as compared to a hard ferromagnetic layer have got transmitted. This is what we saw. And what will happen to the spins of the opposite direction? They will get reflected. And as they get reflected, they get accumulated in the soft ferromagnetic layer. And as you can see, what gets accumulated in the soft ferromagnetic layer exerts a torque on the magnetization of the soft ferromagnetic layer, thereby switching the direction of magnetization of the soft ferromagnetic layer from up direction to down direction. And that is how we went from the parallel configuration to the anti-parallel configuration, or from the low to the high resistance state, to the application of a reset current which is pointing towards the hard ferromagnetic layer to the soft ferromagnetic layer. Next, we will see the set process. In the set process, exact similar things happen, but now the direction of the current has been flipped. Now the direction of the current is from soft ferromagnetic layer to hard ferromagnetic layer. Therefore, electrons will flow from right to left. So this is a charge current electrons, equal number of upspin, downspin. Let's see what happens to the animation. Whatever had the same spin configuration as that of the pinned layer was easily transmitted. Let me show you again. See, this is easily transmitted. However, whatever has opposite spin configuration to the hard ferromagnetic layer gets bounced off right from this particular interface. And the accumulation of these upspins results in a torque applied to the soft ferromagnetic layer or free layer, thereby changing the orientation of the magnetization of the soft ferromagnetic layer from down to up direction, therefore switching the device from high resistance state to low resistance state. And this was the great discovery of spin transfer torque, especially applied to magnetic tunnel junctions, that the magnetization switching in the free layer can happen very easily by just switching the direction of current. An important thing to realize, however, is that the magnitude of reset current is generally more than the magnitude of set current. This is because in the parallel state, the resistance of the MTJ is low. So a given applied voltage leads to a smaller spin accumulation across the barrier. Whereas in the anti-parallel state, the resistance is higher, producing a larger spin polarization and a stronger torque per unit current. And therefore, it is easier to switch from anti-parallel to parallel, which is your set, rather than from parallel to anti-parallel. Okay, so with this concept of spin transfer torque, we got our second generation of MRAM, which is called the STT MRAM or the spin transfer torque MRAM. Here I have represented the STT MRAM or spin transfer torque MRAM in the 1T 1R configuration. So we have looked at 1T 1R configuration several times, so I will not repeat it again. As you know, the bit line is connected to one of the ends. The drain is connected to the other ends of the magnetic tunnel junction, whereas the gate serves as the word line. And what is really fascinating is, since write happens through the magnetic tunnel junction, as we saw in the previous slide, the path for the read current and the path for the write current is the same. So there is no need to have separate read and write word lines. And this really helps your scalability also. So the read current flows in this direction, and depending on the reference current, the sense amplifier judges whether it is in high resistance state or low resistance state. Let us look at the write operation a little bit more carefully, thereby revising our concept of spin transfer torque. In the set cycle, you have to go from the anti-parallel state to the parallel state, therefore switching the device from high resistance state to low resistance state. This is done by applying a positive bias on the bit line, whereas you keep the source line grounded. Therefore, current flows from the free layer to the pinned layer, and the electrons which have the same polarization as your pinned layer are easily transmitted, therefore flipping the direction of your magnetization of the free layer, whereas those having opposite polarization as compared to the pinned layer are getting reflected away. Next, we will see how the reset happens. The reset happens by applying a negative bias to the bit line. Therefore, current flows from higher potential to lower potential. Therefore, electrons having same polarization as your free layer get easily transmitted, whereas those having opposite polarization get reflected away, thereby flipping the polarization of the free layer from this direction back to this direction. So the key advantage of the second generation STT MRAMs is that you are really able to control the write current by scaling cell area. Therefore, area scalability has improved for STT MRAMs from almost 50 to 100 F squared in toggle MRAMs to 20 to 40 F squared in field MRAMs. Not only that, the scaling of these devices has been really fascinating. All your major companies, whether it's Intel, TSMC, provide MRAMs at 22 nanometer node, and the future roadmap is also to go at 12 nanometer node. So therefore, STT-MRAMs is the success story in commercialization. That is what we will see in our concluding class, which is the next class of MRAMs. But before that, we will also speak about the third generation of MRAMs, which is called the SOT MRAMs. So that is Pin Orbit Talk SRAMs. Thank you very much for your attention in this class. See you in the next one.